In this video lecture, we are going to see the definition of Laplace transforms and Laplace transform of some elementary functions. Now we are going to see the definition of Laplace transform. Let f of t be a function of t defined for all t greater than or equal to 0. Then the Laplace transform of f of t is denoted by L of f of t and is defined as L of f of t is equal to integral 0 to infinity e power minus st f of t dt, provided the integral converges for some values of s where s is a parameter. It may be real or complex, and the Laplace transform is denoted by capital F of s. Now we see the existence of Laplace transform, that is the sufficient conditions for the existence of Laplace transforms are f of t should be continuous or piecewise continuous in the given closed interval a comma b where a greater than 0. Second one, f of t should be of exponential order. Now we see in detail what is piecewise continuous function. So we have a answer. A function f of t is said to be piecewise continuous in any interval a comma b if it is defined on that interval and is such that the interval can be broken up into a finite number of subintervals in each of which f of t is continuous. Next one, exponential order. A function f of t is said to be of exponential order if limit t tend to infinity e power minus st f of t is equal to 0. Now we see Laplace transform of some elementary functions. First example, find L of k where k is a constant. We see the answer. By definition, L of f of t is equal to integral 0 to infinity e power minus st f of t dt. Therefore, we can substitute f of t is equal to k, then we can get integral 0 to infinity e power minus st k dt. K is a constant, so we can take outside. So we can get k into integral 0 to infinity e power minus st dt. We integrate this, we can get e power minus st by minus s integral over 0 to infinity. Apply the upper limit and minus lower limit, we can get L of k is equal to k by s. Similarly, we can find L of 1 is 1 by s, L of root 2 is root 2 by s, and also L of minus 2 by 3 is minus 2 3 by s. The second example, find L of e power at. Solution. By definition, L of f of t is equal to integral 0 to infinity e power minus st f of t dt. So we can substitute f of t is equal to e power at. So then the integral becomes 0 to infinity e power minus st e power at dt. So we simplify the power, we can get e to the power minus s minus at. Then we can integrate with respect to t, we can get e power minus of s minus a into t by minus of s minus a. So apply the limits, we can simplify, we can get L of e power at is equal to 1 by s minus a. In the same way, we can find L of e to the power minus at is equal to 1 by s plus a. The next example, find L of cos at. So by definition, we have the Laplace transform. So here we can substitute f of t is equal to cos at, so that we can get integral 0 to infinity e power minus st cos at dt. So we can integrate this integral by using the integral formula integral e power ax cos bx dx. So that is e power ax by a square plus b square a cos bx plus b sin bx. So we can integrate this, we can get e power minus st by s square plus a square into minus s cos at plus a sin at. The limit is 0 to infinity. So applying the limits and simplify, we can get this. That is, finally we can get L of cos at is equal to s by s square plus a square. In the same way, we can find L of sin at is equal to a by s square plus a square. We move to the next example. Find L of sin h at. So here we can apply the trigonometric formula sin h theta is equal to e power theta minus e power minus theta by 2. So the given problem becomes L of sin hat is equal to L of e power at minus e power minus at by 2. That 1 by 2 we can take outside, and then we can have L of e power at minus e power minus at. That Laplace we can operate inside. We get L of e power at minus L of e power minus at, and applying the formula we can get 1 by s minus a, 1 by s plus a. We simplify, we can get L of sin hat is equal to a by s square minus a square. In the same way, we can find L of cos hat is equal to s by s square minus a square. And now we are going to see one important definition, namely gamma function. The gamma function is defined by gamma of n is equal to integral 0 to infinity e power minus x, x power n minus 1 into dx. We have some of the results. Gamma of n plus 1 is n into gamma n. Gamma of n plus 1 is equal to n factorial. Gamma of 1 by 2 is equal to root pi. Next example, find L of t. So we write the formula L of f of t equal to integral 0 to infinity e power minus st f of t dt. Then we put f of t is equal to t, so that we can get integral 0 to infinity e power minus st t dt. So we put a substitution, put st is equal to x, so that we can get s into dt is equal to dx. Once if we change the variable, we have to check the limit also. So when t is equal to 0, x is also 0, and t is equal to infinity, x is also infinity. Therefore the integral becomes L of t is equal to integral 0 to infinity e to the power minus x, x by s dx by s. This 1 by s square we can take outside, so that we can get integral 0 to infinity e power minus x, x dx. We have to integrate this integral by using gamma integral, so that 1 by s square integral 0 to infinity e power minus x, that x we can rewrite x to the power 2 minus 1 dx. Therefore this integral value is gamma of 2. Gamma of 2 is 1 factorial, so therefore we can get the value is L of t is equal to 1 by s square. So the general formula L of t to the power n is equal to n factorial by s power n plus 1. So we summarize all the results and listed here and we have a property, namely linearly property, that is L of a f of t plus b g of t is equal to a into L of f of t plus b into L of g of t, where a and b are any constants. Thank you for watching this video.